Hello and welcome to our talk. Our paper is called CAT-SQL, Towards Real-World Natural Language to SQL, and this a joint work by Han Fu, Chong Liu, Bin Wu, Fei Li, Jian Tan from Alibaba Group and Jianling Sun from Zhejiang University. Our paper focuses on the task of translating natural language to SQL queries. This task provides a convenient interface to access databases, especially for non-expert users. This slide shows a motivating example from the Spider dataset. A natural language to SQL model typically takes the question and the database schema as input and predicts a SQL query. The database schema contains the table names, column names, and the database constraints. In this SQL statement, there are three major challenges. First, this query contains a nested subquery in the where condition. And second, there is a join of two tables in the subquery. And the third, the model is required to interpret the word official in the question to the Boolean condition in the SQL statement. The natural language to SQL problem has attracted attentions for over 30 years. The earlier methods are rule-based. These methods typically parse the natural language question into an intermediate representation and then develop rules to map it into a SQL abstract syntax tree, and then convert the tree into a SQL query. Such methods work well on a targeted domain, but is hard to generalize across different domains and databases. The recent methods use deep learning techniques and have demonstrated promising results towards tackling the cross-domain adaptation problem. Deep learning-based methods can be categorized into two classes. The first line takes the natural language to SQL problem as a semantic parsing task. These methods utilize the sequence-to-sequence, or sequence-to-tree framework to generate a sequence of tokens in the SQL query or in the abstract syntax tree. Such a method demonstrates promising performance, but it introduces heavy computational overhead and does not guarantee the generated SQL queries are executable. The second line of work, the sketch-based methods, design a sketch template with multiple empty slots and train neural networks to fill in the slots. This line of research typically enjoys great speed benefits since they do not need to waste computation resources to generate boilerplates such as keywords, so that all computation resources are devoted to extract meaningful information from the natural language to complement the SQL query. However, the accuracy of previous slot-filling approaches are typically low compared with the sequence-to-tree methods. The reason is that the sketch-based methods design multiple independent networks for different clauses and thus do not generalize well to complex queries. To address the limitations of existing approaches, we propose a new deep learning-based framework for the natural language to SQL task, and our method is called CAT-SQL. The contribution of our work is fourfold. First, we introduce a novel model to combine the advantages of both sequence-to-sequence methods and sketch-based methods. Second, we propose the semantics correction technique, which adopts the database domain knowledge to improve the executability of the generated SQL queries. And third, the evaluation results have demonstrated that our method significantly outperforms existing solutions on both single-domain and cross-domain benchmarks. And the fourth point is that CAT-SQL also achieves outstanding runtime performance. The throughput is up to 63 times higher than previous approaches. This slide summarizes the technical contributions of CAT-SQL. Compared to sequence-to-sequence or sequence-to-tree models, our CAT-SQL uses a sketch and focuses on generating essential information relevant to the natural language question to complement the SQL query. Compared to other sketch-based methods, the CAT-SQL sketch is more general and can facilitate parameter sharing to improve the performance. And we also propose the semantics correction method, examine whether the generated queries are semantically correct and try to fix the errors. The CAT-SQL is an end-to-end neural network model. The overall architecture of CAT-SQL is composed of four components. They are the pre-trained encoder, the CAT decoder network, the conjunction network, and from decoder network. First, we concatenate the natural language question, database schema, and some additional information into a sequence. The question is a sequence of tokens embraced between a pair of a start token and a separator. The database schema part encodes each table name and column names together separated by another separator token. The additional information is mainly used for generating nested queries, and we will talk about it later. We also use different type embedding vectors to distinguish the tokens of different input parts. The encoder network generates a sequence of hidden states which are expected to contain the semantic information of each input token. In our experiment, we use GRAPPA as the encoder model. GRAPPA is a pre-trained language model consisting of 24 transformer encoder layers. The GRAPPA model is pre-trained on multiple SQL parsing tasks and has been demonstrated to be effective on the natural language to SQL task. The CAT is the major sketch of CAT SQL. Each CAT focuses on one column to be used in the target SQL query. Specifically, a CAT consists of a column name and the corresponding functions including the aggregation function, the condition operator, the value, the AND or conjunction, and the sort order. CAT is a generic template which can fit into multiple clauses including select, where, group by, order by, and having. The design of CAT can facilitate the idea of parameter sharing. SQL generation can be regarded as a task of predicting a sequence of CATs. We use 7 slots for each CAT. If a slot is not used in a CAT, we fill it with the none value. The SQL grammar can be converted into this context-free grammar using CATs. The A query here represents an atomic subquery without nested blocks and set operations. We use a placeholder, nested term token, for each nested subquery. The CAT decoder consists of multiple transformer decoder layers and generates a sequence of CATs. For each CAT, we use 7 independent classifiers to fill in each slot. For each column slot, we use a pointer network to select one column from the encoder hidden states of all columns. The value slot is filled using another pointer network to copy a snippet of text in the question. The other classifiers are independent feed-forward layers. A major challenge of predicting values is that the words used in the question may not match the values in the database. Our approach will examine the database values to improve the accuracy. For each value slot, we compare the word embedding similarities between the literal extracted from the question and all distinct values in this column. The value with the maximal score is picked. We also use another feed-forward layer to predict whether the literal is a nested subquery. For a nested subquery predicted, we use the placeholder, nested term token, to fill in the literal slot, and the decoder will expand it into a complete nested subquery in a top-down manner. As an instruction, we collect the column names used in the outer block and append them to the input tokens when generating the inner subquery. The handling of conjunction keywords is similar to the expansion method of nested subqueries. We build a conjunction network to predict whether a conjunction keyword exists in the query. When a conjunction keyword is predicted, we consider the right part of the conjunction as a nested subquery, and the left part as its outer block. The from decoder predicts a sequence of tables, and we run minimal spanning tree algorithm over the schema graph to generate the joined path. The schema graph is a connected graph and the tables with primary key foreign key relationships are connected. We search for the minimal spanning tree which contains the predicted tables, and the connections in the spanning tree are used as the join conditions. Here we show how CAT SQL works using an example. First we serialize the question and database schema into a sequence of tokens. For each table, we concatenate the table name and the names of all columns in this table. The encoder takes the tokens as input and generates a sequence of hidden state vectors. The encoder output is fed to the 3 decoders. The CAT decoder generates a sequence of CATs. When an end token is predicted, the decoder is turned to generate the next clause. The order of the predicted clauses is consistent with the SQL syntax. The from decoder predicts the tables in the from clause. And we convert the predicted elements into an atomic query using the context-free grammar. The nested term token represents the nested subquery to be expanded in the where clause. To generate the inner nested subquery, we collect the used column names in the outer block and append them to the original input and rerun the model. When the nested subquery is predicted, we use it to replace the placeholder in the outer block to complement the final SQL query. Since all the SQL elements are predicted independently, there could be cases that the predicted SQL query is not executable. To handle this problem, we propose the semantics correction approach to fix the obvious semantics errors. The major semantic correction rules can be summarized into three categories. The first class of rules are designed to handle token-level violations such as the mismatch between an aggregation function and its target column. The second class of rules is from clause revision, which is used to handle the cases when a cat block uses some columns that do not appear in any tables of the from clause, and we will add the missing tables in the from clause and rerun the join path generation algorithm. And the join path revision rules are used to fix the mismatched joins between the inner nested query and outer block. To evaluate the effectiveness of our method, we conduct experiments on both single-domain and cross-domain benchmarks. Single-domain means that the training set and the test set use the same database. And the cross-domain means the databases used during training and inference are totally different. For single-domain benchmarks, we compare our model with classic rule-based approaches. And for cross-domain datasets, we compare with the top-ranked models on the benchmark leaderboards. This slide shows the main results on Spider benchmark. The performance is evaluated using the logical form accuracy and execution accuracy. It can be observed that cat-SQL significantly outperforms existing methods. Especially compared to the previous state-of-the-art approach, Picard, cat-SQL achieves a significant improvement of 4 points. We also list the executable rate of different methods, and cat-SQL achieves a 100% score. We submitted our model to the Spider leaderboard and obtained the results on the unreleased test set. cat-SQL achieved the first place on the Spider leaderboard in September 2022. On the WikiSQL benchmark, cat-SQL also outperforms the existing methods. On single-domain benchmarks, we compare cat-SQL with both rule-based approaches and deep learning-based models. From the results, our cat-SQL consistently achieves significant improvements over the compared baselines across all test cases. cat-SQL also achieves outstanding runtime performance. Compared to other methods, cat-SQL is much faster and requires less computational resource. The reason for the high efficiency of cat-SQL is that cat-SQL generates a cat of multiple elements at each time step, which improves the parallelism at inference. Finally, this paper can be concluded as follows. We propose a new natural language to SQL method called cat-SQL, which combines the advantages of both sequence-to-sequence methods and sketch-based methods. The semantics correction algorithm is proposed to improve the executable rate of the generated SQL queries. cat-SQL is evaluated on multiple benchmarks in this paper, and the experimental results demonstrate that cat-SQL significantly outperforms existing methods in terms of both accuracy and efficiency. So that is it for now, and thank you for your attention.